And our first speaker is Aydogan Ozcan from UCLA. Please join us. He's going to tell us about computational microscopy toward telemedicine applications, and I will greatly encourage at the end of each talk a discussion. We've got enough time. We ran a little, we were actually fast this morning, and so encourage everyone to participate in the discussions, including students and postdocs. Please.
Good afternoon, everyone. It's a great pleasure to be here, and I thank you for the invitation. So in this presentation, I'll go over our research on computational microscopy with a specific emphasis on global health and telemedicine applications. But before I do so, I'd like to actually point to the keynote introduction that was given today regarding the Moore's law and how it's crucial for actually computation of today. Actually, if you look at the Moore's law and compare that to the number of pixels that we have on our cell phones, quite interestingly, the cell phone pixel count, megapixel count, which is shown with the red, has been actually quite distantly matching with the speed of progress of transistor counts in CPUs, which is the Moore's law in this logarithmic scale. That is quite surprising, and I don't know how much it's going to continue further, but it's actually the starting bit of something that is quite powerful for doing computational microscopy, and that's exactly the theme of this talk. Cell phones now are everywhere, and they are getting better in terms of their hardware and software abilities. And believe it or not, we have close to 6 billion cell phone subscribers in the world, and more than 70% of these cell phones are actually being used in developing parts of the world, in parts of the world where infrastructure doesn't exist, but the cell phones work fantastically well with these several megapixel cameras working fine. And that connectivity with the hardware itself and the software opportunities indeed hold numerous potential for telemedicine, and utilizing that as a platform, as a starting base for conducting microscopy, microanalysis, has been the theme of our research at UCLA. And I'll tell you more about what we've done with this idea. And what you see on this slide are some of our gadgets that literally convert a cell phone into a microscope, as shown here. Or if you don't want to modify your cell phone, you can create extremely inexpensive and field-portable architectures that can conduct microanalysis using these standalone units. So I'll tell you more about this platform, which we refer to as Lucas. The first interesting property of this platform is that it's a computational microscope, and it replaces lenses with essentially reconstruction codes. As a result of that, these are very compact and cost-effective. And as I'll highlight in the next few slides, these permit us to reconstruct very large areas, very large volumes of specimen, which is also quite important, especially for sensing and disease detection applications. The technology itself is based on digital holography, but it's not conventional holography. I'll tell more about this. And it makes it quite sensitive to even weakly scattering particles like bacterial signatures. And finally, this platform is quite tolerant to misalignments, as it should be, so that if you were to give this to a non-PhD, there should be no problem of misalignment, or the requirement for alignment is quite loose in this case. Lens-free computational on-chip imaging, as I'll describe more, has a unique angle for telemedicine, but it also enables us to increase our imaging throughput drastically if you're thinking about other applications, non-telemedicine related applications, such as looking at extremely large area microfluidic devices, for instance, for detection of circulating tumor cells. In those applications, computational microscopes also could be quite useful to look at in fluorescence or in bright field modes, very large areas on the order of 10, 20 centimeters square, which is something that I won't focus today, but there is another angle to non-conventional on-chip microscopy that actually ties to extreme throughput imaging needs. Coming back to telemedicine and lens-free imaging, well, we don't have any lenses in our imaging architecture. As a result of that, actually, we only image the shadows of the specimen. What is quite different between your own shadow and a cell's shadow is that we're opaque to light, and then our shadow doesn't contain anything useful. It's pitch dark. But when you look at cells or particles at the micron scale, they are semi-transparent to light. As a result of that, if you look at their shadow, it contains a texture. It's like a textured shadow, which you can treat as a fingerprint of the cell and start doing cytometry based on simply recording shadows, lens-free shadows, of specimen that you place on an imager, on a CMOS imager, that the same thing that we have at the back of our cell phones, the same thing that created that Moore's law scale for our megapixel count on cell phones. And these are some particles that uniquely show the differences between different particle types based on, again, the texture that you get. And if you look at whole blood with the same simple lens-free shadow imager, you'll be seeing shadows of specimen, in this case red blood cells. Every now and then you would be seeing white blood cells with distinct shadows. And that's a starting base for actually something more complicated in the sense that it can be used as a cytometer based on these shadow differences, but it starts to fail as the density of the cells gets higher, as shown here where the cells are clustering. But that's the time to realize that these dummy-looking shadows are actually quite rich in terms of what they contain, because they contain the interference of the scattered light from the three-dimensional body of the cell with the background light, and that is actually a hologram. So you can actually treat these dummy-looking shadows as holograms, inline holograms of the specimen, and reconstruct their images, in this case red blood cells, and compare against the regular microscope, but of course over a much larger area, a much larger field of view compared to a conventional microscope, because now you're not restricted to objective lenses. So whether or not it's working on a cell phone, CMOS imager as shown here, attachment, a very lightweight attachment, which has a light-emitting diode, or a standalone unit as shown here, or a backstop system for extreme throughput, this platform actually is based on partially coherent digital inline holography. Actually, holography is a quite well-established science, and we have a pioneer in the field, David Brady, also in the audience here. What we do is a little bit non-conventional holography in the sense that we're not using a laser, we're not using actually coherent illumination. We're using partially coherent light. We could have used sunlight as well, but for repeatability purposes, we are using LED, quasi-monochromatic, incoherent sources, which pick up partial coherence as they travel a distance of a couple of centimeters. That's why this tube length is important. But by the time that they hit the specimen, they have partial coherence. And if you ask the cell itself, it will think it's being illuminated by a coherent source. And that's why their holograms are sufficiently rich for us to reconstruct their holograms. I'll start by showing you some lower resolution images from these holographic shadows. We can reconstruct phase. This is the optical phase that was lost. Once you have the phase and amplitude, you can digitally propagate the image, the waves back and create the image of the specimen. These are some granulocyte images and the subcellular nuclear features and the phase and amplitude. And this is a conventional 4DX.
Scale bars of what?
So this cell is on the order of 10 micron in diameter. And these are platelets, which are 2-3 micron or 4 micron at most in size. These are all acquired with a single light source, but there are different means of improving the resolution of this platform without sacrificing its field of view. And I'll tell you more about how we do this, but just to give you an idea, there are higher resolution versions where you have higher fringes, which can be reconstructed. And now you can see higher resolution features of the specimen, which nicely match the conventional microscope. And I'll tell you more about how we do this higher resolution imaging. Everything is digital. It works as a microscope, but at the same time, it can work as a cytometer, as a blood analyzer. I'll quickly go over some of the results which show that this type of a microscope could work as a cytometer for counting the density of red blood cells or the volume of individual red blood cells, because everything is working as a phase imaging modality. We can also estimate the volume of each cell, and that actually is quite important for various different diseases because the histogram of the cell volume changes as a function of actually certain parameters. And you can do other stuff with the same platform, such as measurement of white blood cell density or hemoglobin content, to conduct essentially blood analysis on the same platform. One thing that I'd like to quickly mention in regards to telemedicine, in regards to global health, is monitoring of HIV-positive patients. This is an important problem because an HIV-positive patient, unfortunately, is run on CD4 lymphocytes. A typical healthy patient would have on the order of 1,000 CD4s per microliter. But once HIV kicks in, this number drops to a few hundred, and that's when opportunistic infections could actually be quite deadly. And you need to, that's why, count every, ideally 3 months, the CD4 lymphocyte count of the patient, but this is done usually with bulky and expensive instruments like cytometers. What we've done is we've combined the lens-free on-chip imaging platform with some spatial microfluidic devices that are disposable that could capture, using some antibodies, specifically from whole blood, these subpopulations of lymphocytes. In this case, we're focusing on CD4 and CD8 lymphocytes to understand how HIV depletes those two lymphocyte types. And once you inject whole blood, you wash it out, you can specifically actually image and reconstruct these lymphocytes. In this case, what you see is one of these microfluidic devices. Each one of these circles is correspond to an antibody island. These are CD4 antibodies. And if you zoom in, you would be seeing their holograms, which can be reconstructed and then counted. In this same chip, we had some CD4 antibodies and some CD8. So we were looking at the ratio of these two to understand healthy versus non-healthy behavior. For a healthy patient, actually, the CD4 to CD8 ratio was very high, as expected. But once HIV kicks in, that ratio dropped significantly, and that's when you have to start the antiretroviral therapy. And that's a good measure that you can actually use these technologies in conjunction with spatial microfluidic devices to actually conduct therapy for these HIV-positive patients. Whatever I've shown you so far in terms of image quality and resolution was acquired with a single light source, a simple LED, a very inexpensive component on the order of $0.2 per piece. And it was actually captured by a regular off-the-shelf CMOS imager, something that you have in the previous versions of your iPhones and BlackBerries. And the resolution was on the order of 1.5 to 2 microns with a numerical aperture of around 0.15. But the big advantage of this platform was its field of view. This field of view is more than 20 millimeters square. If you compare the same numerical aperture that we have in objective lenses, you'll be typically looking at a few millimeters square in terms of field of view. That's where the throughput advantage of computational imaging comes in. We have a larger field of view with the same resolution that a conventional objective lens can provide. Now I'll tell you more about how you can actually improve the resolution of this platform further without sacrificing the field of view. In conventional microscopy, there's always a trade-off between resolution and field of view. If you want to improve the field of view, you would sacrifice resolution and vice versa. It's a fundamental trade-off of conventional compound microscope design. But computational imaging has certain advantages to make this trade-off disappear. To achieve the same field of view, some 20 millimeters square, with a much better submicron, deeply submicron resolution, what we've done is, instead of using a single light-emitting diode, LED, we put here some 20 of them. It's still cost-effective in terms of telemedicine and global health because an LED is pretty inexpensive, on the order of $0.2 per piece. Then we have the microcontroller here, which actually turns on these LEDs one by one. So at a given time, the sample that you insert from the side, which is very close to the CMOS imager, will be illuminated by a single LED, which changes its position based on the microcontroller input. What it does is actually you capture holograms, static holograms of the objects that are being undersampled by the CMOS imager. But then you can synthesize, because the light source shifts, the position of the hologram changes. So it's actually being undersampled in a different way. And you can put together all of these lower resolution undersampled holograms to synthesize a much finely spaced hologram. It's the same trick that's been used in security cameras for more than a decade. If you're in an airport and you're looking at a security camera that's far away from you, your face will be pixelated. But if you are walking and moving left and right while the security camera is recording a movie of yours, then you can actually merge these frames of the security camera to synthesize your face with a much higher resolution than the pixel size or the undersampling gives you. That's called actually pixel super resolution. Much before fluorescent super resolution microscopy has been discussed in the literature, photography people were aware of pixel super resolution techniques. So we're borrowing the same set of techniques here to actually improve the space bandwidth product of on-chip microscopy beyond the CMOS imager. What it does is you start with an image like this, which is a lower resolution hologram. All these fringes are coming from interference of waves, and they are actually corresponding to higher numerical apertures. But some of them are washed away because of the pixel size. Now you can bring them back and synthesize something that was normally lost. Another way of saying this is you take a 5 megapixel imager and digitally you convert that into something like 200 megapixels, which now has much smaller effective pixel size over the same field of view. That gave us the ability to actually look at smaller features, improving the resolution down to sub 300 nanometer with a pixel size that to start with was on the order of 1 micrometers. In other words, now you can reach a numerical aperture of 0.8 to 0.9 across a very large field of view of around 20 millimeters square, where you can now resolve deeply subpixel features based on pixel super resolution. This image has on the order of a gigapixels in it. The big advantage here is that we're decoupling actually field of view from resolution, and we can conduct submicron, deep submicron on-chip imaging over very large areas. And if you zoom in, this is actually a blood smear. This is the same exact sample that you would normally be imaging for diagnosis of malaria. There's a monolayer of cells there, and you'd be looking at red blood cells and trying to spot the parasite infection. Especially for malaria diagnosis, this is an important achievement because the parasite signature appears only 1% of the time. The parasitemia rate typically is less than 1%. That's why you would be normally taking one of these conventional objective lens field of views and scanning it several times to statistically see some of these parasite signatures. Whereas with a microscope design as shown here, which by the way is still less than 100 grams in total, USB powered, you'd be having a very large field of view and easy time to see these parasite signatures in red blood cells. Of course, with a much larger field of view than a conventional microscope, and that's the whole point, the throughput advantage would be helping us to look at rare signatures of abnormal cells, in this case, infected red blood cells. And these are some other samples. This is a pap smear used for screening of cervical cancer. One important advantage that on-chip computational microscopy has is it's seated on the Moore's curve in the sense that every time there's a new sensor that's coming out, without changing anything, you'll be improving your performance. Within just within less than 6 months, with the new sensor as shown here, we can now look at 30 millimeters square from 20 millimeters square to 30 millimeters square without giving away anything while keeping the same resolution at the submicron level. And that's where it gets quite competitive. If you don't want to restrict yourself to CMOS images, if you can work with CCDs, then you have a whole new world in the sense that now you can look at a field of view that has, instead of a millimeter scale bar, now it has a centimeter scale bar, and now you can look at, in this case, around 18 centimeters square field of view. Again, a typical objective lens with a similar resolution would be looking at a couple of millimeters square, so this is on the order of 3 orders of magnitude wider field of view compared to a similar resolution. This one actually is on the order of 1.5 gigapixel in this image. Because of its simplicity, you can actually do more than just microscopy from a single projection. You can do tomographic imaging. Very similar to how X-ray CT works. You can have your light source, which in this case is an LED, and rotated along an arc and an orthogonal arc to conduct limited angle tomography. In this case, we like the dual axis because limited angle tomography has artifacts because of missing frequencies, and you can now make up some of those artifacts, correct for them, using a dual axis scheme. In each position of the source, you jitter the light source left and right a little bit so that you can synthesize a super resolved hologram of that cross section and then advance to the next one. And each one of these angled illumination cases is still an inline hologram. It follows the same reconstruction principles. What I show here in this movie is actually a tomogram reconstructed across a very large field of view on the order of 15 millimeters square and a millimeter depth of field. So you're looking at around 15 millimeter cube, 15 microliters of volume, where we're slicing it with different Z slices here, submicron level, to see these 5 micron particles embedded in a gel in this case. And this is actually a tomogram of a C. elegans, a model organism that's highly popular, especially for neuroscientists, where you are tomographically imaging it using a lens-free on-chip microscope. This was slightly tilted, so this part will be in focus first, and then the remaining parts of it will get in focus. Because of the simplicity of its architecture, you can actually create a field-portable lens with tomographic microscope using the same principle. This is the design of that field portable tomographic microscope, where you load the specimen from the side. There are a bunch of LEDs, which are controlled by a microcontroller. So this movie shows you what's happening. Every time there's a single light source that's illuminating the sample using a multimode fiber. The sample is inserted from the side as shown here. This movie is a little bit more difficult to see, but if you follow this arc, it's moving left and right by an electromagnetic actuator, so that you can actually, without touching it, move the fiber source to create subpixel shifted holograms of the same scene. And then you advance to the next angle and create super resolved holograms with this field portable design. This I'll skip. It's another movie which shows actually tomographic slicing of a volume using this field portable design. So what I've shown you was mostly bright field imaging over a large volume, over a large sample area, so that we could benefit from the high space bandwidth product of these sensors and what we can do on them by using some super resolution techniques to even further improve the pixel count and the space bandwidth product of the final image to ideally a gigapixel or higher. We've also done some other work on converting conventional cell phones into fluorescent microscopes, fluorescent cytometers, and sensors, or even a simple rapid diagnostic test reader, which is an application to read this. I won't go into the details of that, but there is some more exciting work that could potentially bring more advanced microanalysis tools around the cell phone, because the cell phone itself is a great tool, especially in remote and underdeveloped parts of the world. But this picture actually reminds me of the transformation that we had from going from the PC to the internet, in the sense that we're now making, just like PCs were extremely inexpensive and compact, which led to the fact that we could buy them in our homes and then play with them. And then the network emerged by combining the PCs together, forming the internet. With these technologies running extremely inexpensively on cell phones, within the next decade or so, will potentially increase the number of personal microscope users, personal microanalysis tool users by several orders of magnitude. Then, if they're connected, that could create something that could be quite more valuable than one of these individual devices. So that you can now have an internet, which I call as the micro-internet, which looks at, for instance, spatiotemporal distributions of things that you image at the microscale and nanoscale using these inexpensive and widely deployed technologies from our lab or from others in the world. It will create its own challenges. It will create a lot of data that we don't know how to analyze, because with these gadgets, we will create a lot of data, several megapixel in a single image. Who's going to look at them? Who's going to analyze what is being imaged? One big problem that we have today is digital technologies increase rapidly, but the expert training does not. And there's a mismatch between qualified personnel to look at and diagnose or label these images versus our technologies. And machine learning is not yet there. So in the last few minutes, I'll tell you about a platform that we, with this exact vision in mind, we launched this spring of 2012. Actually, we created an interface which you can log in yourself through biogames.ucla, which gives you microscopic images of cells. In this case, in this particular focus, we were looking at red blood cells, and we were trying to diagnose malaria. So the user, the gamer, would be logging in, and will have a game like this, which the user can actually, after a very brief training, could select which cells are infected and which cells are not. And then, of course, we have servers which will collect all the data. But once we have one of these games being played, we have control images in each one of these screens that we exactly know who's messing with us and who is not. So that I can tell among this crowd of gamers who are really playing well and who is not playing well based on some control images that we know the exact labels. So far, this platform has been out there for a couple of months. We have gamers from 70 different countries, and so far we've generated more than 1.5 million cell diagnoses. And this is actually the map of these gamers. We treat each gamer as actually a telecommunication repeater, where there are some images that need to be labeled and decoded. In this case, they are microscopic images of red blood cells, which we do not know the label for, if it's infected or not. Each gamer has a prior probability of error because we had some control images, so we can exactly tell, roughly, estimate these error probabilities. At the end, it's a decoding problem, very similar to how our conventional telecommunication network is working for creating a diagnosis out of these gamers. The results came out quite interesting, that actually using even undergraduate students at UCLA from the School of Engineering, only 20 of them collectively could come as close as around 1% of the diagnosis accuracy of an expert pathologist at UCLA. So collectively, 20 undergraduates, again, non-medical, School of Engineering, could be quite competitive because of the fact that they are now correcting their errors through a statistical model. Of course, this won't scale up because FDA will never approve any diagnosis based on undergraduate students. But this was a starting point for us because we knew that trained personnel in global settings is very close to what we expect from an undergraduate. Actually, we did this study. We gave similar interfaces to experts. These are the top-level experts across the world on malaria diagnosis. And we tested their self-consistency and accuracy and how they compared with their peers. We've seen a lot of inconsistencies, that the same guy, the same expert was labeling something and then changing his decision after 1,000 more images has been played. And they don't agree with each other. So experts are not consistent and there's a lot of error that's being hidden. You can always hide an error at the single cell level by looking at more cells. That's at the cost of money, because if you spend more time on a single slide which contains thousands of cells, you can always hide your individual errors at the single cell level. But we want to create something that's going to work with actually half-trained or half-expert people that we can outsource these images. So the idea was, we also did this study, which is soon going to appear online. We gave our images to a bunch of experts, and their training level was also predicted based on control images. And at the end, we were looking at the diagnostic accuracy of the crowd based on learning their statistical behavior. And the results turned out to be quite promising in the sense that in a crowd where there was some range of expertise in terms of this is the maximum and this is the worst case of each group, we could achieve actually a diagnostic accuracy overall, which is much better, even the best of the group. And that's the starting bit of something that's much smarter than actually having an individual expert diagnostician give you his or her opinion. You can have 3 or 4 that work pay per image, that will be working with you part-time, that you could have the infrastructure at the server level to decode their answers so that you can arrive at the correct diagnosis much faster and much appropriately. This may not scale up for the United States, and that's not what we're aiming for. It may be very well scaling up for actually resource-poor countries where maybe there is a couple of pathologists per country. There are literally small countries like that where there's an immediate shortage of certain expertise in that setting. That's why these digital super pathologists could be quite useful. The same platform also could be helpful for training the next generation of pathologists, because imagine that you have these games that you can download in your iPad and play with them to understand your training level, how it degrades over years. And we can exactly give you feedback on which cells you make mistake and how you compare against your peers. So there's a lot of room for actually improving the digital accuracy and the quantification of pathologists when it comes to doing these routine single-cell level analysis every day. With this, I'd like to conclude, and thank you again for your invitation.
That's really great. Thanks a lot. Very fun, very exciting. And now, questions and discussion. Yes?
This diagnosis of infected cells is a great machine learning problem. What are the barriers to any of that?
Great question. Actually, we were thinking of the same. I mean, if you look at this slide, which I didn't talk, actually, this is where we think the future would be lying. Machine learning would come in, and it requires very well sorted gold standard image data sets for it to work very well, which doesn't exist today. When we created this game, we looked at Google and all the digital resources for red blood cell images to see what we can crop and use in our games. There wasn't more than 100 that we could use. We needed at least 8,000, 10,000 range. We literally created our own by having an army of undergraduates scan these malaria slides one by one, and we created that. That's the starting base for various different diseases today, as far as machine learning is concerned. And that's why such an interface would be quite useful to create the gold standard labels for various different conditions that the machine learning can be then taking over. Then down the line, you would be having a hybrid system, which is going to work with a machine learning interface, which always gets better as it goes on. But it's going to handle the big load of data, gigapixel images that comes from a point-of-care office. Then it's going to give a certain decision on the ones that are way above a threshold. The ones that it cannot decide, it's going to pass on the experts. And then the experts will collectively diagnose it, hopefully, using a smart statistical learning approach, which will exactly know how well they were doing this week. Then that information goes back to the point of care, together with the crowdsource, together with the machine learning result. And then part of it goes back to the machine learning again, to fine-tune your results. And I think that's where, to manage this big data that's going to be generated and that's being generated, we need this hybrid approach between machine learning and a smarter way of crowdsourced pathology.
More. Tyler.
Yeah, can you just give a quick overview of the super resolution method? Basically, you say you're jittering. I mean, how much accuracy do you need with that jitter? And then do you do a statistical correlation, or what method is used?
Yeah. So that's actually one of the nice things about this platform, because let me show you this slide again. There's a big demagnification between the shift of the light source and the shift of the shadow. The reason being, this is the tip of the fiber array, right? These are multimode fibers, and you see only one of them illuminating. The distance between the tip of this fiber and the sample is on the order of a couple of centimeters, let's say 4 centimeters. The distance between the sample and the active area of the CMOS is a millimeter range. That 400-fold reduction in the magnification means that if I move my source by 400 microns, it moves by 1 micron. That makes my illumination condition quite loose. I've never worked with this precise micrometer, because large movements correspond to small movements on the shadow end. And that's where I think we've benefited significantly in terms of precision of this thing. And we estimate all of these shifts actually based on correlation at the hologram level. We don't assume anything here, but even if you were to assume, you don't need something very precise because of the demagnification.
Cool. Yes?
So this works very well for the cytometry that on the cells on the clean vector. Can it work with cells in the tissue slice?
It would work, because this is a transmission microscope, and it requires a hologram formation, which means there needs to be a plane wave or a reference wave that you can account for, either spherical or plane. In this case, it's plane wave, which makes our reconstruction nice and easy. But for tissue, you need something different. We've been asked this tissue, can you image tissue, especially histopathology slides? And for that, actually, we've changed the geometry, and we've borrowed from the rich literature of holography. In the case of a tissue slide, you can actually create a reflection mode microscope, where you place your sample here, it's opaque, or it's dense enough that it doesn't let the light penetrate without significant distortion. Then you'd work with the reflected light, and then there's a clean mirror here, which creates your reference, and you record the interference hologram, and then you reconstruct. So this is actually a reflection-based microscope, very similar to the previous one, except it's working with dense tissue. Its resolution is not as high as the previous one, because we haven't implemented super resolution here yet, but there are opportunities here to push some of those same techniques to improve the resolution.
Perhaps you mentioned this, but is there some thinking about how to add at least some sort of low-resolution spectroscopy capabilities to look for biomarkers or something like that? Perhaps
Great.
dichroics or something?
So in terms of biomarkers, let me quickly go to this slide. So we haven't done spectroscopic imaging, but to understand what we are imaging specifically, we've applied some of these ELISA assays. Let me go over, it's probably not in this slide. Sorry for just taking one more.
No problem. I asked the question.
Okay. So,
That's the long film.
So for that type of work, we rely on surface chemistry and ELISA type of assay. So what you see here is actually a fluorescent imager which is imaging microtubes here. So it's a capillary actually. You can barely see this, but there is something that's glowing here. It's the blue excitation light. If you look at what's going on in this cartoon, there are microcapillaries which on their surface, they have some antibodies which are specific to a certain species of, in this case, E. coli. So you flush your liquid and then it's bouncing to the walls and then specifically being captured. Then there are some quantum dots which also have the secondary antibody. You flush it again. Then all of a sudden, each one of these capillaries will be glowing under correct excitation with the quantum dot emission, in this case reddish. So based on this intensity per microcapillary, you can actually understand something that microscopically would be impossible unless you have this specific conjugation. So some of the tricks that we've used for that, handling that type of problems, involves surface chemistry, but there are spectroscopic ways of doing this, and there are other groups who have tackled bringing high-end spectroscopy tools, also working on cell phones for global health applications.
Great. Anything more? One more.
A lot of your shadow images look like reflection interference microscopy. Is that what you're using?
No, these are transmission in the sense that, so there are cells, and each one of these is actually a scattering center. There's tiny in cross-section, so you can ignore absorption. So there are scattering centers, and there is, of course, phase that's due to the refractive index contrast. So the wave that penetrates through these objects picks up a wavefront distortion due to scattering and phase mostly. Then you want to get that wavefront distortion coming from the cell body and image that. That's your information. To image that, you rely on the fact that it propagates. As it propagates, due to diffraction, it enlarges, and then it overlaps with a reference wave. And that reference wave is the wave that has passed through the entire slide, like a plane wave would, without picking up distortion. That's an assumption, but that's a very well assumption, at least for the resolution level that I'm referring to. And then you record the interference between those two wavefronts, and that's the starting base. That's the starting base of what we call holographic reconstruction, and you basically tackle the problem of lost phase there. And you try to recover the phase using some iterations. There's phase recovery in optics, especially holography, is a quite rich topic where you can find lots of different methods. We also apply different methods in our own work. But one simple method that works very well is to go back and forth between the hologram plane and the object plane, each time throwing a random phase. But once you come back, with the wrong phase, you will be having an incorrect object bound, and you can go back with the correct object bound, which can be loose, and then you will have a perturbed phase, which is better than nothing. You keep the perturbed phase and then replace the amplitude with the measured one, because measurement is the most reliable one, and then you can iterate like this. In around 10 iterations or so, you can converge to the correct phase. Uniqueness is a problem, but for most practical objects of interest, you don't get apples for oranges.
Let's thank the speaker again. That was great.